Hey there, YouTubers!
This is our sun, a G-class star. It's 4.5 billion years old. Except its inner workings are no different than this star, a blue F-class star. The inner workings of this star are, just as I said, no different than our own sun. But we have to go deeper to understand. So when you look up at the night sky, you see billions and billions of stars. And there's so many on orders of magnitudes so large that your brain doesn't have the mental capacity to fully process that information. And then the distances between us and them, their sheer sizes, how hot they are, and how massive they are, these numbers are so big that our brains simply cannot fathom the scales of which the universe plays on. But we can try and bring these stars down to Earth and break them apart. And that's what we're going to do in today's video. We're going to break the stars apart. We're just going to talk about what a star is and how they're classified, how they're born, and how they basically work. And then we'll talk about their untimely demise. So by the time of this end of this video, when you look up at the night sky, you'll be fearful. But you may also be thankful.
So what is a star? Well, in layman's terms, it's basically a huge ball of hot hydrogen and helium. Now, this hot hydrogen and helium is going under a process called fusion, and I'll get to that in the next scene. But this is about all you need to know for now. Anyways, now into classification. Stars were originally classified solely based off brightness. However, this proved problematic because as stars age, their brightness changes, and with distance, brightness also can change, and so it ran into problems. So they then tried solely basing it off of spectrum lines. Oh boy. So, I've talked about the spectrum before on my channel when I talked about it in my color video. In that video, I tried to split a beam of light into the spectrum, the rainbow, its different colors. However, I failed. But with the right instruments, if you point a prism at a star, you can see it split out into a spectrum. However, you'll see lines in it. And these lines represent different elements that are surrounding the sun or the star and have been excited. So, medium-sized stars will have very strong spectrum lines because they're hot enough that they can excite just about every single element around them. And really cooler smaller stars are unable to do this, so they have very weak, if to no, spectrum lines. However, really hot stars, big ones, really bright ones, are too strong, too bright, too hot, that they excite the atoms so much that they strip the electrons away, leaving behind just the protons. Thus, they have very weak spectrum lines because they're not exciting anything. They've obliterated them, essentially. So, the modern classification system is based off of luminosity and temperature, and each star can be given its own letter, going from biggest and brightest to smallest and coolest, O, B, A, F, G, K, M, or a fun little acronym for those who need to remember for school, O, be a fine girl, kiss me. Now, girl can be whatever your preference is. So how are stars born and how do they work? Well, stars are born in massive dust clouds called nebulas. These massive dust and gas clouds cover large areas of the cosmos and are vast in size, stretching upon light years and light years. Here are some pictures. Wow, aren't those beautiful? My favorite's probably the Eagle Nebula, or the Pillars of Creation to be more exact. The pillars are just a small portion, but yet are still light years across. Absolutely beautiful. In these dust clouds, gravity seemingly randomly pulls particles together. As these particles get closer and closer and closer, they begin to have a single point that seems to have a greater gravitational pull. And they pull in more and more particles. This causes that gravitational pull to increase because it has more mass. And it pulls in even more and more and more. Eventually, at the center, the heat and pressure begins to be so great that the probability of two hydrogen atoms coming together and staying together in a process called fusion becomes so great that this can happen all the time and can be self-sufficient. And now I've alluded to how fusion works long enough. It's time that we actually break it down. So for the simplistic sake, I'm not going to talk about fusion of how to create iron. That is the heaviest element that can be created in a core of a star. And there are a few other elements that can't be created in this core of a star that are lighter than iron, but that's a whole nother thing. But anyways, all you need to know is that when two hydrogen atoms get close enough, and with enough heat, enough pressure, they eventually stick together to form a helium atom, which is heavier than the one before, and then helium can form, and then when two helium atoms get enough heat and pressure, they come together, and so on and so forth. But when these two hydrogen atoms come together, they release a massive amount of energy. And this release of energy is key to how stars function. Now, when this fusion first takes place, we call this a protostar. Now, a protostar is just a little baby star, and it doesn't become a main sequence star until the solar winds generated by the fusion inside its core. When the solar winds are strong enough to push away the gas cloud to reveal our new star, and it will begin to use up its hydrogen and age. Now, this hydrogen releases energy. This has an outward force, and this counteracts the inward force of gravity pushing down in it. Now, eventually, this outward and inward pressure becomes imbalanced as the star ages and helium ash, quote-unquote, builds up in its core. Eventually, this process becomes so imbalanced that the star will die in a either very peaceful, or a boom. Why, hello there. I have my fun fact book. I'm in my fun fact chair. That means it's time for a fun fact. Now, I guess it's a fact, but it's more about the scale of what we're working with here. The sun. If it were 1.5 millimeters in diameter, then the largest star in the known universe, Betelgeuse, would be the size of this green ball, which is half a meter in diameter. So if the sun was 1.5 millimeters, Betelgeuse, the largest star in the universe, would be half a meter in diameter. Isn't that just fascinating? So now it's time for the more depressing part of our video with a little hint of optimism. So we'll start with K and G class stars and how they die. Our sun is a G class star. It's about 4.5 billion years old. And it has another 4.5 to 5 billion years left of its own active life cycle. But in that time, it's going to undergo a few changes. As hydrogen in the core begins to be exhausted, the helium ash will become unstable, and it will collapse in. This will cause the outer layers of the sun to expand. This will consume Mercury, Venus, and potentially Earth in this process. And then eventually, after this, the sun will go under what's called a helium flash. In this, 40% of the sun's mass will be converted into carbon almost instantaneously. And the outer layers will slough off, forming a planetary nebula. And at the center, a white dwarf. At this point, all fusion has stopped, and the white dwarf will eventually spend the next 100 trillion years cooling off, leaving behind just a chunk of carbon. An M-class star will simply just die. Once all of its hydrogen is exhausted, it'll cool off, and it'll just be helium atoms floating across the universe. Now, an F-class star gets a little more interesting. It follows the same way of a K and G, except there's no white dwarf left. There is no planetary nebula, and it will fuse further than carbon. It will fuse up to iron. Except that last reaction, that last fusion reaction that creates iron, releases no excess energy. Thus, that outward pressure from the energy stops, and the star collapses in on itself. This collapse will send reverbs across the cosmos in an explosive event called a supernova. This will obliterate any sort of solar system it may have had, leaving behind something called a neutron star. And a neutron star is so dense that the protons and electrons have turned into neutrons, and the only force keeping it from collapsing further are the actual neutrons' repulsion themselves. As gravity pushes further and further, these neutron stars will eventually just cool off and die, because there is no fusion happening anymore. Now, A, B, and O class stars, the lightest of A's will maybe form neutron stars, but it's almost guaranteed that the rest of A's, B's, and O's will form black holes. Now, this happens when the density at the center of the core has become so great that the density is infinity. This is the center of a black hole, a singularity. And the edge of a black hole is the event horizon. The event horizon is the point at which the escape velocity of the black hole is the speed of light, and nothing can go faster than the speed of light. Thus, this is the point of no return. And a black hole isn't forever. A black hole will slowly emit a type of radiation, Hawking radiation. And as Hawking radiation will expel what's left of the mass of the black hole, and eventually there will be nothing left. When every single bit of matter in the universe, every single atom has been consumed by a black hole and then re-emitted by Hawking radiation, there's nothing left. This is one proposed death of the universe. Well, here we are at the end of the video. In all the hype around the heat death of the universe, I neglected to mention that supernovas are so powerful that they're able to create heavier elements other than iron. They create copper and uranium, and they create other elements that simply can't be fused to the core of stars, like beryllium. And considering that we don't need beryllium or these heavier elements like copper and uranium, we still need those heavier stars that aren't like our sun, ones that can form oxygen, because we are hydrogen, carbon, oxygen, phosphorus, these heavier elements that simply cannot be created by stars like our own. We are stars, and we will eventually probably be stars again. The atoms that make up us were at one point forged in the heart of a dying star and spread across the universe by a supernova, only to be randomly collected again by gravity, and our star breathed life into the solar system, and we were eventually 4.5 billion years later born of our mother's wombs, made of stardust. And when we die, and our sun dies, eventually it'll probably reformed into another star. And eventually those stars will form black holes or be consumed by them and re-emitted by Hawking radiation, and we will be nothing but nothing itself. But in the meantime, I'd like to thank you all for watching. Please like, comment, and share. New videos every other Friday, 4:30 p.m. Central Time. And as always, good night. Step 3. Maybe I should consult my book. Oh, hi there! Didn't see you there. Bet you didn't see me, because I know nobody's watching. Ha 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 ha. Because I never want right now, like how to make money from YouTube. Yeah, you should totally subscribe, please, and check the playlist wherever it's gonna pop up. Jeez, this is getting awkward. Bye.